Hey everyone, in this video I wanted to dive into where are the keys in passkeys. We hear a lot about passkeys, how we should use them, how they're phishing resilient, how they're using public-private keys and asymmetric cryptography, but where are the keys actually being stored when we leverage passkeys? So I thought in this video we will dive into it. Now remember, when we leverage a passkey, we're leveraging that passkey. Imagine we're talking to some internet, a specific relying party. So when we think of a relying party, it's a particular web presence. For example, we often go to a website. I can think it might be www.saviltech.com. And maybe there's a port at the end of it. Maybe I'm using a non-regular HTTPS, so it's 8443. Now, the relying party we're creating the passkey for has a relying party ID, an RPID. The RPID must be a subset of the URL for that particular relying party, for that web presence we are going to, be it Microsoft or Google or GitHub or Saviltech. So if I was going to this site, we're always going to strip off the HTTPS. We're always going to strip off the port. And so it could be just saviltech.com, could be the relying party ID, or it could be www.saviltech.com. But those would be, one of those is what I would pick to be the relying party ID. And one of the things this does is it actually helps protect the user from being tricked. Because when I want to use a passkey, the relying party ID of the passkey has to be part of the URL I'm visiting. So if someone was trying to trick me and was trying to send me to www.savil, but with a 3, for example, or some weird character, well, that Saviltech with a 3 does not include that relying party ID, so it would not let me use it. So it helps protect me as the user from someone trying to trick me to authenticate, which then they go and do something else with on their behalf. So that relying party ID, hey, it's part of the name, that fully qualified domain name that we are visiting. So that's kind of that first block. It's always a subset of the URL. And if I think about the key requirements and the benefits of the passkey actually gives me as the consumer, well, there's 3 bits to it. So I am using a certain client platform. And we're going to dive into this in more detail, don't worry. But I'm on a particular client platform. So that's my device. Could be a PC, it could be an iPhone, could be a Google phone, whatever that is. And then there's the client itself, the thing that's talking to it, that speaks the web. And then, of course, the other component is when we're talking about this is we have our authenticator as well. So we draw our authenticator. Now, that authenticator, again, can make many different forms. It could be some sort of USB device. It may speak near-field communications. It could be a TPM within our device itself. It could be our component, our keychain in our iPhone. It could be the Microsoft Authenticator app. But we have this authenticator as well. And there's 2 key ideas around when I want to use the passkey, which is being housed in this authenticator, with any relying party via the client platform. The first one is proximity. So I must have proximity between the authenticator and the client platform. Now, from a protocol perspective, this is the Client to Authenticator Protector, or CTAP. And this would be used if, well, the authenticator is not inside the client. So this could be, is a token device. So I have to go and insert it or have a Bluetooth connection or near field communication. So they have to be pretty close between them. It could be the authenticators on my iPhone, or I need a Bluetooth connection to my client, my PC, to use the passkey. So what this does is it stops me being tricked by some bad actor that tries to get me to authenticate their machine, their client, that's hundreds of miles away. It can't, because the authenticator requires that proximity to whatever client platform it's currently doing that authentication for. The other requirement we always have to have is if I think of the user, well, that user has to always perform some user gesture. So it has to be a deliberate action. It's the user promise. They have intent that they want to go and use the passkey for whatever this action is. And this could be some sort of biometric check. It could be a PIN as well. But there's some assurance that, yes, I actually want to go and use my passkey right now. So we have these three actors involved as part of leveraging our passkey. And as we talk about where are the keys, actually, let's go up here. Well, there's two keys. In the public key cryptography, there's always a public key and a private key. So I can think about, well, yes, the public key, we'll draw on this side for no particular reason at all. But we have the public key, and then we have the private key. And we're going to draw the private key in our nice universe color. So we have our private key. And with this asymmetric cryptography, the whole point here is if I have some data, doesn't matter what this is, but let's say I have my data and it's just ABC. When I encrypt it using my private key, it results in some encrypted data. So we'll just say it's XYZ. With asymmetric encryption, if I now take that and give it to another party, only the equivalent public key can then decrypt the value. So in this case, the public key could then be applied to this value, and I would get ABC back. And what this proves, if I'm this end, because the public key anyone can know, I know whoever performed this encryption, essentially I'm creating a signature of the data, they must own the private key. Because I know this public key could decrypt it, and the only thing that could have done the encryption would have been the private key. So whomever I'm talking to at this moment, I know they have possession of the private key. So this is a huge point. Now, often on the internet, if I want to send something encrypted to someone, we kind of do the opposite. We would encrypt the data with their public key, because then only they could decrypt it. But in this case, I'm trying to prove I have ownership of the private key. So I encrypt something with the private key, and then, hey, people with the public key can decrypt it successfully, which means, hey, only the private key could have done that encryption for it. So this is a key fundamental factor to everything about really modern cryptography. Okay, so where are the keys? We talked about there's this private key and the public key. And obviously the private key, therefore, is super, super important. So the easiest way to understand where are the keys is if we look at these parties involved. So obviously we have the client platform. Now remember, the client platform is made up of the client device. So that could be the smartphone, the PC, the operating system on it, and then the client. And the client is responsible for really marshalling the inputs that it then will go and send to the authenticator and then return the results, all based on the web authentication specification. So I think as we go through these communications, we're going to have the client platform. And then, of course, we have the authenticator. Now, again, the authenticator could be within that same device. It could be hardware, it could be software, it could be a separate device. There's a lot of flexibility in how I actually leverage these, but the authenticator's role is to facilitate the creation of these keys and then assert possession to prove I have possession of the private key. So then we have this idea, okay, we have the authenticator component, and we have that line of communication. And then again, we have the relying parties. We talked about the web presence, selection of sites, all under a certain domain that we want to go and talk to. And to help understand where the keys are, let's look at the idea that I'm a client and I want to create a new passkey for this relying party, for this set of websites, everything under Microsoft.com or Saviltech.com, although not many people would want to go there, please. So as the client, I'm talking to the relying party and I'm saying, hey, I would create a passkey, please. So passkey, please. The relying party will send back a challenge. Now think of the challenge as a string of cryptographically random bytes. The goal is to be something that can never be used more than once, a nonce, which stops a replay, i.e. some bad actor can't take this challenge that I'm going to go and sign and try and use it for another request in the future. So this says, hey, here's your challenge. And I would like a public key, please. So give me a public key that is going to be associated with all of the things we're going to do. Now, on the client platform, I might have multiple authenticators registered. So the client platform will go and check what it has. It will identify the one I want to use. It may even prompt me, hey, which one do you want to use? Do you want to use Keychain, if I'm on an iPhone, for example, or the Microsoft Authenticator app? It may give me that choice. And once I make that choice, its responsibility as the client on that client platform is to really forward this on. So it's going to include that challenge again and that public key request. So now on the authenticator, this is really a key part of what's going to happen. It's the authenticator's job to prompt the user for a gesture. So, hey, enter that PIN, give me that biometric. And then it will create the private public key pair. So it's going to go ahead and create my private key. And it's going to go ahead and create the corresponding public key. So it's generating those two things. Now, once it's generated those, what it's now going to do is send back in the message, because now it has these available. I'm going to send back to my client that can then forward that on. That challenge that we had, it is going to sign it. It's going to basically encrypt it using the private key, and it's going to include the public key. What it can now do, the client will take those materials, send it to the relying party really exactly as it is. So exactly the same, we have the challenge, it's encrypted. Make sure I draw the key the right way around with the private key, and it's sending the public key. The relying party, having the public key, can decrypt this that was encrypted with the private key, this signature. The values will match the challenge it sent. So it's like, okay, this is good. I know that this party actually has the private key. And often when you go and create these new passkeys, you'd have authenticated already using a more traditional. So maybe you had a username and password and a traditional MFA initially to prove you are who you say you are, or some decentralized identity. You had some way to prove you are this human being that should have this. But now on this time, the relying party, well, they're going to now store that public key, associate it with your identity, which is the key part about this, and fundamentally send back a, yep, good, you are registered, you are good to go. So that's the very high level generalized, but the flow of what happens. And realize when I actually want to use a passkey, it's basically exactly the same thing. But instead of me saying, hey, I want a passkey, please, I say, hey, I want to authenticate, please. This will know who I am. So it's like, hey, here's a challenge. I want you to sign this so you can verify yourself. So then the client says, hey, I want you to sign this challenge with my private key. I would have to then do that user gesture, the PIN or the biometric. So I have an intent. It would then sign the new challenge. And here's the signed data. Here's the signed data. It would be able to validate that matches the stored public key, and I would be authenticated. So now I would be logged in and good to go. And so if I look at this picture and I want to answer, where are the keys? Well, the private key stays on the authenticator. So the private key is here. The public key is stored by the relying party. So the relying party has all of the public keys for all of the people that create passkeys for that presence. But realize it's a public key. It's not like the old days where, hey, I'm a site and I would store credentials for everyone that used my site. If I got hacked, that hacker now has all of the credentials for all of the users that have used my site. If this gets hacked now, the attacker has a whole bunch of public keys. It's useless. They really can't do anything with that. Each user on their authenticator has the private key, which is really the important part. So this is another huge benefit when we think about the passkeys. It actually gives us protection from when these relying parties could get compromised. Now, there is one additional point I guess I should mention just to be very, very thorough. So I drew this idea of the private key lives on the authenticator, which is 100% true. But there are two types of device key. We do have the idea, and it's maybe the original, the traditional idea, where we have something called device bound. So with device bound, that key never leaves the authenticator. So as an organization, for example, I know where the passkey is at all times, and that can be very important in certain scenarios. So if I think about the idea of, well, like the USB type little keys, it could be a TPM bound inside a PC, it never leaves that authenticator. Now, the authenticator could still be roaming. What does that mean? Well, imagine like this key, technically I could connect it into different clients. So I can use my passkey on different machines to facilitate authentication. My phone. If my phone, I'm using a passkey on it, I could establish Bluetooth connections with different client devices. But the passkey itself, that private key, never leaves that authenticator. It is bound to it. Now, the other type is synced. Because imagine this scenario for the regular consumer. They change their phone, they forget to do some actions, they forget to create a new one before they delete their phone. They're now locked out of the service. So this is fine when there is some administrative capability to, if it gets lost, it can get recreated by some other mechanism. In Entra, I could do like a one-time passcode, a temporary access pass to get the user bootstrapped to go and create the passkey. In the consumer world, that would get very, very messy. And so the other thing we can leverage here is synced. So with synced, let's draw the idea that I have some particular cloud service. And that's going to be way more common again on those consumer, on my iPhone, on my Google device. So now I could think about, well, I actually have, I've got my iPhone, and the key is synced into this particular ecosystem. And then it can be synced to other devices linked to the same account. And I'll have the key here as well. Now, in this case, the stewardship for the key is that particular platform. So there is one entity protecting it. It's Apple. It's Google. But now as the consumer, my passkey will be available on all of my devices. But generally it can't go beyond a particular ecosystem. So it could be my iPhone, it could be my Mac, it could be Android to Android, it could be Windows to Windows, but it can't cross those because of the stewardship. But this is much nicer for a consumer scenario where, hey, they may have multiple devices, they may replace a device or lose a device. So this is a way to help make it more available while still assuring the integrity of the passkey, because it's still owned by a particular ecosystem, still responsible for a particular ecosystem. So in this case, where are my keys? In the synced scenario, my key is also being stored. My private key is still being stored in some cloud service that's part of my ecosystem, and then synchronized to my other devices that are under my same account. So, hey, that they can be a little bit more broadly available. And that's the answer to where are my keys. When I'm using passkeys, the public key will be stored by the relying party for which I've created the passkey. The private key always lives within the authenticator. But if I'm using a synced passkey, it would also replicate to my cloud service, be available on other devices in the same ecosystem. So as a consumer, that's a lot more flexible and more friendly for me to use. But hopefully you see that with the protections it gives, so hey, I require that proximity so the user can't be tricked to go and authenticate some bad actor hundreds of miles away. The user can't be tricked on their local machine to go to some bad site that's trying to use a slightly weird character to get them to authenticate, because it won't let them. It will say, no, the relying party ID is not part of this URL you're going to. You can't use this passkey for that site. It's obviously easier for the user to use. And if the relying party was compromised in some way, they just get a whole bunch of public keys. They can't do a huge amount with it. So there you go. Sometimes understanding these things helps you feel a bit more comfortable with it. And that was the goal of this video. Until next one, take care.